Запись пошла, все видно.
Отлично. Yeah, so we can start with this field of rational numbers, and we ask how could we construct some examples of say, well, some cyclic, for instance, that is abelian Galois extensions of Q. Well, maybe some, yeah, some. Maybe not all, but maybe we can start with some examples, and then we can try to see whether we can construct all of them, all cyclic extensions, say of degree, I don't know, of degree. Well, we can start from 2, yeah. Well, the first case is 2, yeah. So how could you construct these ones? So you have to add something to Q, yeah? So the question, what could you add to Q, to the rational numbers, so that the resulting extension will be a...
Square root of 2 or something like that.
Yeah, okay, square root of something, yeah? Square root of something, and doesn't really matter what you take, just you take any D...
Of some non-square.
Yeah, D non-square, yeah. A non-square. Okay. And actually, you know that, well, actually, we may say that D is, if we multiply D by square, then the extension will not change. Yeah, so actually, we may think that this is an element of Q modulo the squares. Yeah, so this is just any integer. Well, maybe -0, yeah, -1. So, and if you take distinct elements of this quotient, then you get a distinct extensions. And by Kummer theory, do you remember what is the Kummer theory? It's just that you see, the
Could you
point is
please
that
repeat the Kummer theory? So what it
yeah.
consists of?
So the Kummer theory says that if our so we have Galois extension. Well, actually, sorry. Not a Galois extension, just any extension. Yeah. So okay. A field extension. And we assume that K contains a primitive, so n is an integer. Well, maybe at least 2, otherwise if n is 1, it's not interesting. So is an integer. K contains a primitive root, nth root of unity. And you see that, for instance, Q contains the second primitive root of unity, yeah, so it which is called -1, yeah. So when n is 2, then the only condition is that our characteristic is not 2. Yeah. Now, sorry. I'm writing something strange. Unity, nth root of unity. Okay, that's it. That's the end of condition. Then any abelian extension, abelian. Well, then maybe not any, but there is a bijection. Then there is a bijection. There is a bijection between a billion extensions, extensions of k in L of period n, and what? And subgroups of what? Of the following quotient. We consider those elements that are nth powers in L but belong to K, and modulo nth powers in K. Subgroups of this group. Okay, so you remember how it's constructed. So if you have a group here, so set H, then you just associate to this group the following extension. You just adjoin to K all elements of all nth roots of elements of H. Yeah, so H is an element in this L nth power K, such that its class modulo nth powers of elements of K belongs to H. Yeah. So, for instance, if example, if n is 2, then any extension of period 2, for instance, of degree 2, so any degree 2 extension of K is given by adding a square root, square root of d. So if n is 2 and the characteristic of K is not 2, because this is precisely the condition that K contains a primitive second root of unity, and second root of unity is just -1. Second primitive root of unity, So okay, so for the quadratic extension, it's clear. But what if we are interested in extensions? So this is Kummer theory. And what happens if we are looking for cyclic extensions of degree 3? So can you construct this? So in principle, you can try to apply again Kummer's theory, but the subtlety here is that there is such you see that there is this condition that K contains this one, that K should contain nth primitive root of unity, But well, it's but anyway, you can try to reduce somehow to this situation, So what do you think of this? So the question: how to construct at least one cyclic extension of Q with of degree 3. Well, can you construct at least some?
Could you remind us what does the cyclic extension mean?
Cyclic means So a cyclic extension definition. You see that the word is adjective. Adjective cyclic or abelian means what you see that here we talk about cyclic extension, here about abelian extension. It means that
This adjective
so you see that
is an adjective before the Galois group of this extension, or
yes, that's right. So it means that it is a Galois extension with a cyclic Galois group or with a abelian
okay,
Galois group.
thanks.
So yeah, so Galois extension with an well with a cyclic or abelian Galois group. Okay, so the question is how to construct sorry, Galois group. So how to construct such an extension?
Well, the first thing that I want to do is add the nth root of some element, for example, the third root of 2, for example.
So the cubic root of 2.
Yeah.
Well, you see the problem here is that this extension is not Galois. So if you, of course it is, so is not Galois, is not Galois extension. That's the problem. Extension, because you see that you may embed this field can be embedded into the real numbers, yeah. But the other roots of unity, if you embed your field into the real numbers, then the other roots of the polynomial of the minimal polynomial x cubed minus 2, they are imaginary. Yeah, so you cannot permute the roots. Yeah, so this extension is not normal. So that's the problem. But you see that actually
And
maybe
nth root of unity
okay.
times nth root of unity like e 2p I over n.
Sorry. Yeah. Okay. So you mean primitive?
Yeah,
A
nth primitive
primitive.
root of unity.
Okay.
A primitive
And
complex root of unity.
well, it doesn't matter because yeah, they are all well in some sense. So a primitive root, yeah, a primitive nth root. And what will you do with this primitive nth root? Nth root of unity, and what would you do? If you just add adjoin this to yeah. So this one, of course. So this is a Galois extension. By the way, do you remember what is the Galois group of this extension?
The group of permutations. I know.
No, because you see the point.
It's a cyclic group.
No, in general.
No, it's uh, integers modulo n.
Not really, because well, for instance, if n is 2, then of course, then if n is 2, then this is just minus 1, so this is the same, yeah. So this group is trivial,
Yeah.
so it cannot be Z mod n.
mod phi n z mod phi and well Euler's function or
Well, it's not true. It's not true. It's not true. You see, so let's try to think where this. You see that we to define so uh, to define or describe. Let's call it simply G. To describe an element of G, it suffices to say what is the image an element, say sigma of G. It suffices to say what is the image of this primitive to determine zeta n sigma. Yeah. So what could be this zeta n sigma? So what it should be another primitive root nth root of n root of unit. Yeah. Okay.
okay.
So it is all roots of all primitive roots are powers of each other. So they are powers for some a, which is residue modulo n, but there is one condition. Yeah. So this residue. So you see that this residue should be invertible. You see?
Mm-hmm.
So actually, and when you know what is the image of one primitive root of unity,
Then we
then
know all the others.
yeah. So yeah, this is the reason.
So this group is the multiplication group of
Yeah, it's a multiplicative group of
z
the
modulo n.
residues. Yeah, modular. That's right. Yeah. So it is not. You see that you said that it is residues modulo the Euler function, but it's not true because this group is not cyclic in general. So it's not isomorphic. It's not isomorphic in general to z mod the Euler function. When yeah, because it's more. You can see for instance, when you z mod 15. What is z mod 15? It is by
Z mod 3 times
yeah, it is z mod 3 by z mod 5, but you consider invertible elements. Yeah, so z mod 3 invertible elements here are z mod 2.
Z mod 2 and z mod 4.
Yeah, that's right. Yeah, you see that it's not the same as z mod so it is not isomorphic to z mod 8.
Mm-hmm.
Yeah, that's the point. Okay, so yeah, that's right. So so this way we can construct extensions. So we see that we have constructed extensions with such groups. Z mod n, well, the multiplicative group of Z mod n. So the question is how to construct an extension with the cyclic group of order 3, for instance. Yeah. So that's the oh yeah. So we have a quite big supply of extensions of, say, these ones, yeah, and we know they are Galois groups, and it remains to construct. So now we want to get Z mod 3. So how could we do this? Can you see where this Z-mod 3 could come from groups of this type. Maybe.
Perhaps it's Zmod. Zmod 5 is not well, it's Zmod 4. Well, I want to say that it's Zmod 4 multiplication group, but there's a problem that
No.
only two of the elements of this group are invertible.
Yeah, maybe I should ask you what is the Galois theory? Galois theory. What is the Galois correspondence? What is this?
Could you please remind us?
Okay. So we can see the Galois extension. Well, maybe I should try that this only finite. So far we didn't discuss the infinite Galois correspondence, but maybe we should first try to play a little bit with the usual finite Galois correspondence. Yeah. So first of all, yeah. So we have a Galois extension. So L over K, which means that so a Galois extension, the finite Galois extension. Extension. This means that we have so that K is the fixed field of certain group, of a finite group. So namely a group of all automorphisms of L over K. So this is a finite group. And then the claim is that there is a one-to-one bijection. There is a bijection between intermediate subfields. Intermediate subfields and subgroups of the Galois group. Yeah, namely to each subfield you associate automorphisms automorphism group fixing this subfield, and to each subgroup you associate the fixed subfield of this group. Yeah. So this is the Galois correspondence, but you may also restrict this correspondence to certain intermediate subfields. Let me specify that it is intermediate subfields of this extension. But you may consider only those intermediate subfields that are normal over K. So subfields of L normal over K. Over K. And actually this correspondence induces a bijection between such subfields and normal subgroups. Normal subgroups of G. Well, because of the same reason, yeah. So, namely, what happens if the subgroup is normal? Then you can say that so this group subgroup goes to what, to the fixed subfield, and the claim is that the Galois group of this fixed subfield over K is just the quotient of G by H. Yeah. So this is this is a Galois extension or normal. In our case, normal is the same as Galois extension. So maybe I should write. This is the same as.
One second, please. How do we read? So it's G. The Galois group of LH over K is G modulo H.
That's right. Yeah. Yeah. I mean, it's a claim. I mean, it's well, it's an exercise. Exercise. Yeah. Because you see that actually, you know that all exercise this follows from what? From at a certain point we have checked that any automorphism of a norm of an yeah. So if we know that that our extension is normal, then any automorphism of this extension extends to any bigger normal extension. Yeah. So this means that that the natural map. So the natural map is surjective. The natural map from G. You see that G induces an automorphism. All elements of G induce automorphisms of the fixed field. Yeah. So the natural map from G to automorphisms of this fixed field to A is injective. Sorry, surjective. Surjective. And its kernel is precisely H. Its kernel is H. Yeah. So that's how it works. Yeah. So this means that that you can construct. So when you want to construct a Galois extension with a given Galois group, then you can present this Galois group as a quotient of some other maybe bigger Galois group by a normal subgroup. Yeah, and in the case, of course, in the case of abelian extensions, any subgroup is normal. Yeah, so you cannot, you should not care about normality, yeah, of your subgroups, just a subgroup. Yeah. So the question is how to. Yeah, so actually what we can do, we can construct at least some abelian extension and then pass to some intermediate subfield of this abelian extension. Yeah. And by the way, do you remember so far we have constructed not only we so far we have not only Kummer theory. Yeah, Kummer theory actually here in the case of in the case of rational numbers, Kummer theory doesn't give much because we don't have any roots of unity except of second one. Yeah, second we only have only -1 as a root of unity, as non-trivial root of unity. But if you remember, we have constructed some other. Yeah, so we did construct it, and actually we have already mentioned this. Yeah, this one. Yeah, so maybe using this one, you can construct or also extension, cyclic extension of degree 3. So what kind of groups can you construct as Galois groups of this cyclotomic extension? Just give some examples for different n.
Of the group or of an extension?
Of the group, because an extension is determined by, well, just give some n. Give
Uh,
some n and
5,
5.
8,
I don't
or
think it's no. It's not interesting because if Z mod 5 is just a cyclic group of order 4,
mhm.
and Z mod 8 is you see that we have to get something which is related to Z mod 3. Yeah, which can be
N
related.
uh, N is 6, for example.
No, because Zmod, you see, Zmod 6 is the group of order 2.
Mm,
So it's not interesting.
Z mod 9.
Zmod 9, okay. Zmod 9 is yes, it's okay. It is Zmod 2 times Zmod 3. Okay. And now now we have to construct an extension. Yeah, so we have, so what does this mean? This means that we have this Galois group so we adjoin ninth root of unity, and its Galois group is Z mod 9 invertibles. Yeah. Okay, and so what? How could we get an extension of Q with of degree 3 using this extension?
Look at the roots of this. Well, no, no,
Actually,
not the roots, the squares.
sorry, squares of what?
Squ Q of psi square. Or well, no, it doesn't make any difference.
Yeah, because you mean some square of this.
So perhaps we have to take some power of Xi9 in order to get to Z3.
No, you see that if you raise zeta 9 to some power, you get another. So if a is it will give you the same is another primitive root of unity, and it generates the same field. Yeah, so it is the same as zeta 9 if A is invertible, yeah, if Z mod 9 invertible. Yeah, so it doesn't make sense. So I propose to look at this correspondence. Yeah. So or
So
maybe
take Z3, well, 0, Z3 as the subgroup, and then we somehow have to see, well, we'll have to find out how does the Galois group affect the zeta 9.
you see that we want that quotient will be so we want the quotient to be equal isomorphic. So G mod H uh, should be isomorphic to Z mod 3. Yeah. So what should be H?
Z mod 2.
Z mod 2. Yeah. So what is Z mod 2 in terms of this group? This is a group of so we want a group of so when, this should be a group of two elements. Yeah. So we just have to find an element whose square is one.
Mm.
Yeah. Yeah. So this is so that's right. So H is just plus or minus one. Okay. All right. Now. What is the action of this group on our cycloatomic field? So how does H? Well, so maybe we should. Well, maybe it's. Well, it is an isomorphism, yeah. So maybe let's write this way. So it is an isomorphism. More or less canonical, but still. Let us call this element the non-trivial element sigma. So what is the action of on? So what is Z9 sigma? What is this? How does sigma act on primitive roots of unity? So what is this? So you see, it should be non-trivial automorphism whose square is 1. Yeah, it is called -1. Yeah,
Then it's
actually,
zeta sigma equals
zeta 9.
zeta sigma minus 1.
Yeah, inverse. Yeah,
Yeah, sigma
yeah.
inverse.
Okay, all right. So the question is, what is the fixed field? So what is the fixed field? So we
Wait, zeta 9. You mean that zeta
what elements are fixed by this?
by this group? It's zeta 9 and zeta
No,
9
zeta
inverted, or
no, no, no. No, zeta 9 is not fixed because
hmm
it goes to its inverse. Yeah,
hmm.
so it's,
Then there are no elements fixed by it, excluding unity.
you see, when a finite group acts on an abelian group, then you can there are several options to get elements fixed by this group. For instance, you can sum up the elements of its orbit. Yeah. Well, if your maybe the digression. So fixed subgroups, subrings, subfields. of a finite group. So we assume that H acts on something. Well, let's call it M. Then the elements like sum over all. I'll just take any element M, any element of M, and sum up over the H orbit of M, MH, and then it is fixed by H because by this subgroup, because when you apply well, let's call it psi. So since when you apply some element of H to Xi, then you just get a permutation of these elements. So it will be H M H prime H, and this is the same as sum over all. We just change the order. MH, and this is Xi. Yeah. So for instance, you can do this way. So this is for any abelian group, yeah, for any abelian group M, when this sum makes sense, yeah. So sum makes sense and doesn't depend on order, yeah. So you assume that this group is abelian, or maybe not even group, but just a semi-group, but abelian commutative. So for instance, if you have if in the case of ring you have a multiplication, instead of sum, you can consider the product, yeah. Or in the case of subring and or subfield, you can consider in the case of a ring of or subfield, you can consider elementary symmetric functions of yeah. So instead of instead of sum, instead of sum, take any symmetric function. Symmetric function like sum of sum of all products of pairs. Yeah, for instance, if your group is finite, then you just consider a product over all pairs like this, hi times mhj, yeah, something like this. Yeah, and this also will be fixed by h. Okay, so in our case, our group is consists of two elements. So what could be an element that is fixed by h? Can you produce at least one of them? So what is written here? In the case when H is our group of two elements and M, so you have to choose M. Well, but just take anything you want. For instance, if you
Okay,
take
then let's take let's take all powers of zeta.
zeta 9, yeah, and what will be this? This will be just yeah, and you know that this is called cosine. No, twice cosine, yeah, but it doesn't really matter. Oh, let's call it twice cosine. Cosine of well, it doesn't. What I'm writing doesn't make sense until we embed our field into the complex numbers, yeah. But 019, yeah, and actually it's one can show that it is actually yeah, that's it. Yes, that it
And
is.
once again, please, how did we get that zeta sigma equals zeta inverted?
This is yeah, but that's the question. How actually it was you who said this.
No, I said that zeta sigma is zeta sigma inverted. Well, it's sigma inverted applied to zeta.
Yeah, but sigma inverted is the same as sigma because it is a group of two. It's an element
Mm-hmm.
of all. But actually, I don't understand the difference between sigma and sigma inverted. You see that at a certain point we have constructed an isomorphism. Where is it? It's here. Yeah, it's here. That this one. And I thought that we have discussed this. So you see that how do you want to describe all automorphisms of nth cyclotomic extension of the rational numbers, yeah? To describe them, it's sufficient to describe the how do automorphism act on nth on some nth primitive root of unity, yeah, zeta n, and this element, this primitive root of unity should be sent to another primitive root of unity, and any other primitive root of unity is a power of our fixed one, yeah, zeta n. And this power is an element of is an invertible residue modulo n, yeah. So that's how we get this isomorphism. Okay.
Seems to be.
And here you see that here we already have identification of automorphisms acting on our fixed primitive root of unity with powers.
Mm-hmm.
Powers where these powers are invertible residues modulo n. Yeah, for instance, in our in our case that was -1. Yeah. Okay.
Okay, yeah, understood.
Okay. So yeah. So we have this. So this element is fixed. So of course, so this is fixed by h. But then it is sufficient to conclude that this is the equality because so there are no other elements which are not in the subfield generated by this element by this cosine because you see that this is an extension of degree where is it? Yeah, so it is an extension of degree 6. Yeah, so the order of this group is 6. Yeah, and therefore this mm, this so this so of degree, so this field is of degree 3, and this field is also this field is of degree well, you see that it is of degree greater than 1, so over q. This field is of degree greater than 1, and at most 3, yeah, because it is fixed. It is a subfield, yeah, It is maybe, yeah, actually it's maybe I should say this way, that it is a subfield here. It is of degree strictly greater than 1, and this degree divides 3, yeah, and therefore it is of degree 3, degree 3, and therefore it is the equality. So this here is the equality because they are of the same degree over Q. Okay, so that's how you construct how you construct this extension. And can you describe what? Yeah, can you describe this somehow? What are automorphisms? Well, of course it's yeah, maybe it's too obvious. Yeah. Well, maybe you can find another example, another extension of degree 3. You see, we have so far we have considered n equals to, well, 2, 3, 4. What else could we consider? Maybe even 8. Yeah, we have considered 8. It was not good, but still, I don't remember where it was. Well, maybe I have erased this. It was here. Yeah, but doesn't matter. Okay, so what about? Well, can you give more examples of extensions of cyclic extension of degree 3? For instance, well, you see that we have considered many cases: 2, 3, 4, 5, 6, 8, 9. But why haven't we considered the case of n equal to 7?
Mm, perhaps. Well, its invertible group consists of 6 elements.
Okay.
And here we can take here we have a subgroup that's isomorphic to Z mod 3.
We do have, but
It
strict. Yeah, okay, but
it consists of 0, 2, and 4.
wait. You see that actually we need well, in a sense, it is equivalent, but strictly speaking, we don't need a subgroup. We need a quotient. You see, like here, we didn't look for we were not looking for a subgroup of order 3, but we were looking for a quotient of order 3, so we were looking for a subgroup of order 2.
Hmm.
You see?
Okay, here we have a subgroup of order 2 that consists of 0 and 3.
No, you see,
Or
we don't have such a group. It's an isomorphism, yeah, so we should think of this group, so
okay,
which is
okay, the image of this group consists of 0 and 3.
okay, and what is in
Modulo
these terms, what is this? You see that here we have a natural isomorphism between invertible residues, modulo 7, and the Galois group. But we don't have a natural isomorphism between the Galois group and the residues modulo 6. Because you see that the point is that we have to, at certain point, we have to use Galois correspondence. So we have to uh, take invariance of a certain subgroup of, well, in this case of order 2. But if you think in terms of residues modulo 6, then it is clear what is the action. But here, if you identify, well, you see that this isomorphism is very natural, yeah, because the residues modulo 7 act on the seventh roots of unity just by raising to the corresponding power, and it's clear. So when you look for certain subgroups, please try to look inside of this group and not because otherwise it will not be clear how to take invariance of the cyclotomic extension. You see?
I seem to get a bit lost.
Okay. Uh, you see that we obtain our extension, this L.
Yeah, here we take some subgroup, and the extension that corresponds to it is um, the extension, the fixed subfield of this group.
Yes.
So
Yes.
we want a group of a subgroup of order 2
Yes.
for G modulo H to be or to consist of 3 elements.
Yes. Yes, that's right. But to
So
at certain point,
I don't see a problem here. That's the problem.
no, there is no problem. The only problem is that in which terms are you going to describe this subgroup H?
For me, it would be easier to describe it in terms of Z modulo 6.
You see that there is no natural isomorphism between Z mod 6 and the Galois group.
But there is an isomorphism between some subgroup well between the Galois group and the invertibles of Z modulo 7.
Yes, that's right.
And also there is an isomorphism between um, invertibles of Z modulo 7 and Z modulo 6.
Yeah, but it's not natural.
And how do we define a natural isomorphism?
Natural means uh, natural means natural in the sense that um, there are um, there are mm, well if you have two concrete groups, then of course you can well, you see
So
that
the problem is I don't see a problem here.
okay, all
So for
right. Well, I ask you a concrete question. Can you give an explicit Galois extension with cyclic Galois group of order 3? So I ask you a concrete question, and so I expect a concrete answer.
It's z plus z square plus
I don't understand. So what
okay,
is
okay,
what you
okay,
see?
okay. Let's
I have
it's
to put here something.
yeah. Here I put z plus z squared, where z7 squared and
You mean zeta? You mean zeta?
sorry,
Zeta?
zeta.
Zeta plus
Zeta
what?
plus zeta squared and plus zeta, well, the fourth power of zeta, or something like that.
No, I don't understand. This or something, this element or something else.
Um, an element that looks
And
like
how,
that.
how did you get this? I don't understand.
Uh,
Where this element come? Where?
no,
Uh,
no, this is how I want to. Wait, it's for the. No, we want an element that is a sum of two powers of zeta, because we have only two elements in our group. So it's zeta 7 plus uh, zeta 7 inverted.
yeah, you see the problem. The problem is that actually you don't need to identify. Here you have to find element of order. There is only one element of order, non-trivial element of order 2, namely
Mm-hmm.
minus 1. Yeah.
Yeah, and
So this, so of course this is this element. Yeah. So actually it is again cosine of pi over 7. Yeah. So and then of course this this group um, is cyclic of order 3. Okay. But maybe I should ask you what is the how to describe the Galois group of this. This you see that there is no much difference between this example and that. The only difference is that there it was 2 pi over
so
9 and
perhaps the main idea is that we take all the elements of order um, no, all such elements that which orders of which multiplied by 3 in this example will give us the order of Galois group of this extension. Well, the order of z modular n invertibles.
yeah, but you see that actually you are looking for a subgroup of index 3. Yeah, so it
Perhaps
should be.
perhaps it's called this way.
Yeah, so for instance you can well, you can of course what else can you 13, yeah, so for instance you can go further to um, yeah, but maybe we should discuss first of all the Galois. What is the action of? So we know that this is. So first of all, how could you describe this Galois group and its action on the field? So how could you describe this group? So we know that it is cyclic of order 3. Yeah, but how could you describe it? So what? Well, uh, you can think of this as what as. I don't know. You can say that this is it is of order 3, so it will be identity. some element and it's square, yeah, or square or inverse. Yeah. So how could you describe this? So what would be the action this of one of these non-trivial elements on this element of the field? Yeah, how could you describe this?
Perhaps it's a cosine of 4p modulus
Yeah, that's right. Yeah. So
velocity.
it's like, yeah. So it's like squares. Yeah. So it's like squares in the square residues. Yeah, in modulo 7. Yeah. So they are just multiplying because 2 cube. Yeah, 2 cube is 1. Yeah. So it just multiply and this. Yeah. Okay. All right. Yeah. Yeah. And all right. So that's how it works. So is that clear or maybe? Yeah. Okay. Actually, we can also try to look if there are other mm, uh, ways to construct. You see that so far we only use cycloatomic extent. Cycloatomics means that um, they are subfields of extensions obtained by adjoining some roots of unity. Yeah, but you may ask whether there are other extensions. So maybe are there any other extensions of degree? Uh, are there uh, non-cycloatomic? No, non-cyclo cycloatomic extensions. How do you think? Sorry, cyclic cyclic extensions of Q of O of Q of degree 3. Degree 3. How do you think?
And what's the difference between cyclotonic and cyclic?
They have nothing to do. You see that cycloatomic means that they are obtained by adjoining roots of unity. Cycloatomic means so. Yeah, maybe I have not given this definition. An extension is cycloatomic. Cycloatomic if tension of K. Okay. If it is contained in K of certain roots of unity. Yeah, so it has nothing to, well, it has something to do with cyclic extensions, but not too much. Yeah, but the point is that yeah. So the question is, are there any other? So for instance, if this degree was 2, then so example maybe. Yeah, maybe I should give you an example. Um, extensions of degree 2. Degree 2 extensions of Q. So as you said, so they are. So what are degree 2 extensions of Q? As you said, they are just do you know why there are no others? Do you know why there are no other? Well, this is just Kummer theory, yeah. So I mean, of course you can do this, prove this directly, but I mean, if you don't want to prove anything, then you just say that it is Kummer theory because we do have primitive second root of unity, namely -1. Yeah, it's here.
Mm-hmm.
Okay, so it's but in principle you can prove this directly that any degree 2 extension is obtained by just adjoining some square root of something, and which you may assume that it is. Yeah. So okay, but I claim that all these extensions are cyclotomic. Do you know this? That they are contained in certain uh, in certain field generated by roots of unity. Do you know this? No. So. Mm, so the claim position. So let's square that this is contained in certain. Let's see. So it is contained in zeta p, where and maybe what else? Yeah. So if
Where
well,
B is prime, or
no, well, maybe let me put it here, big N for some n, for some integer. I'm sorry, just a second. Yeah. So the claim is that this contained in some cyclotomic extension, so it is a subfield of generated by some primitive root of unity. Well, this means that for some integer n. Yeah. Yeah, maybe 2. Okay. Yeah. So the proof is quite so simple. Namely, you just so you assume that D is a product of a certain, well, this plus or minus, yeah, plus or minus product of what? Of some over some primes, yeah, over some, yeah. We may assume that it's not important here, but we can assume that it is square free, so it is a product of certain primes, yeah. It's sufficient. It is sufficient to treat the case of 1 prime. Yeah, it suffices to show that square root of p or minus p belongs to a certain cycloatomic field zeta of something. Well, plus or minus doesn't matter because we can always adjoin here square root of -1, so it's the only thing we have to do is to show that square root of p or minus p, whatever we want. So show that at least one of one of a and p belongs to this cycloatomic some cycloatomic extension. Okay, so now how do we construct this cycloatomic extension? We use what is called Gauss sum. It is some finite version of the gamma function. So it is let's call it g. Well, maybe not g, but gamma. Yeah, gamma will be a sum over all residues, non-invertible residues, modulo p, z mod p, of Legendre symbol times primitive ith root. Yeah, so maybe let me put here p. Okay, yeah, to the a. Okay. Now let's try to calculate gamma square.
And how
So you see
does
this is
the Legendre symbol work?
what is
What is the Legendre symbol?
so the Legendre symbol is equal to 1 if a is a square and -1 otherwise. So it is minus. Yes, if it is not square. Okay, now, yeah, so now let's try to calculate the gamma square. What is gamma square? It is the sum over pairs A and B. And so it will be, yeah, and the point is that it is so is a homomorphism. Is a homomorphism from the multiplicative group of the residue field to the group of two elements, plus or minus 1. Okay, yeah, so it will be AB. So this will be the Legendre symbol of the product, and here we will get A plus B. Well, in principle, sometimes it is convenient to extend. Sometimes it is convenient to extend this to 0 by 0. So if A is equal to 0, then we put this symbol to be equal to 0. Yeah, and then this is convenient because you can then you can remove this invertible sign. Yeah, so you can sum over all elements of your finite field. So AP, AP. Okay, so we can remove this sign, and now now we can change our indices. Yeah, for instance, what? For instance, let's try to. Yeah, if we take here. Yeah, maybe we can do this. Yeah, so you see that the options are either sorry, a bit confused. So if yeah, maybe we can keep so far. Yeah, maybe we can keep. Yeah, so let's denote AB by C. AB, or maybe yeah. So AC. Okay, so this will be C over P. Then zeta A maybe yeah, maybe it's easier to put here B over A. I mean, it doesn't change anything, but it will be slightly more convenient. So it will be A.
Then it will be A square over P.
Yeah, but you see that it doesn't change the squares. If it was a square, then it will be square. So it is. It factors through the quotient by the squares. And this is an okay. So yeah, so it will be AC, да? Yeah, AC. Okay. Sorry, here we should put star. Okay. Now, we can. Yeah. So this is correct, I think. Yeah. So now you see that we can sum over all. Yeah. Yeah. So we have to. Yeah. Yeah, we can consider the sum over all a's. Over all a's. Yeah, maybe we can sum over all residues. The same sum, but after that we will have to remove sum over all a's equals to 0. Yeah, so let me write this. So this will be C O P. Here it will be A1 plus C minus so A should not be equal to 0, so we have to subtract this. Sorry, it's here, it's not clear. 1 plus C here. Yeah, so minus the case where A is 0, so it is sum over all C. C over P, yeah, sum over, yeah, like this. Like this. Okay. Yeah, I think it's okay. Yes, is that correct?
Wait,
Yeah.
it's AC in FP minus this sum.
Yeah, so I think it's
and why did we get the okay.
you see we have here we sum
Yeah,
over
I
all
see.
non-zero,
Uh,
and
wait, didn't
we don't care.
didn't we say that?
You see, when a is 0,
Mm-hmm.
then we get something non-zero here. So we have to
Yeah.
we have to subtract this. Okay.
Okay. Yeah, understood.
Yeah. So summing over all. Yeah. So it will be a sum over all C in F P C over. Yeah. So it will be. Yeah. I'm just rewriting this. You don't really need to rewrite this. I'm just doing some stupid thing. Namely, I'm just putting some brackets. Just I don't know why. Yeah, just like this. Okay, and minus and this is 0. This is 0 because there are the same. There is the same amount of quadratic squares. Sorry, there are the same amount of squares as non-squares. Yeah, so this is 0. So we can forget this. And
Once
also
again, please. Why is the sum 0?
because there is a one-to-one correspondence. Well, it's not one-to-one. If you there is, you see that when you there is a bijection between squares and non-squares. You just take any non-square and multiply all squares by this non-square, and you get a non-square,
Okay.
and vice versa.
Understandable. Okay, thanks.
So this is 0, and now this all these sums. So this is 0, and all these sums are also 0, except uh, uh, if when 1 plus c is not 1 plus c is 0. So this is 0. If this is, you see that this is the sum of all pth roots of unity. So it is 0 if 1 plus c is not 0. And therefore, the only thing
And once again, it's 0 if 1 plus c is not 0, because
because this is the sum of all pth roots of unity.
and that's 0. Okay.
Yeah, and if 1 plus c is 0, then this is p. Okay. So this means that it is minus 1 p times p, and that's it. And you can, well, if you wish, you can write this more explicitly, like minus 1 p minus 1 over 2p. Yeah. Okay, but maybe I was a bit sloppy about. Actually, yeah, maybe I forgot to say that here we somehow assume that
And why
P
is it
sorry, P is should be somewhere we have used that P is
positive?
no P is P is
Well,
positive. I mean even not sorry odd.
it's
So P
it's prime.
no it may be 2.
Okay.
It's not 2. That's I don't know where, but somewhere we have used this. Let's try to see. Let's try to see where somewhere we have used that P is. Um, P is at
Well,
least 3.
uh, We used it when we said
Yeah. It's
something about Gauss sum.
yeah.
In
Residues and non-residues. Yeah, because there is only one
yeah,
residue.
it's when we started looking at gamma square
Mm, yeah. So
because in case p equal to it's
yeah, but maybe this here, this sum is yeah. So this sum is
perhaps the sum turns out to be zero only in case
yeah, yeah,
p is
yeah, yeah. Mhm.
of
Okay, yeah.
course, of course, you see um the Legendre symbol in F2 is always
It's stupid. I mean, it's
nope, nope,
there is no minus one there. Yeah,
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 so
yeah.
it's always a unity.
Yeah. Okay. Yeah. So yeah. So you see that we have constructed. So the conclusion is that gamma gives us square root of this element, which is plus or minus p, and that's what we wanted. Yeah. So this is so. Yeah, so you see that any quadratic, so the conclusion is that any quadratic extension is cyclotomic, so it is contained in certain by in a field obtained by adding joining some root of unity. So what about cubic extensions? Well, cyclic extensions of degree 3. Is it? Well, maybe it's not that easy because yeah, but you see that maybe the proof was rather explicit. Yes, so it was an explicit construction, but maybe maybe it's well, maybe we can stop here, but I would propose you to think a little bit about this. For instance, we could try uh, to see. You see that you can. What is the difference between 2, and 3? In case of degree 3, we need to use a complete description of abelian extensions or cyclic extension of degree 3. We need the square cubic root of 1. Yeah, so it will be, so we can add 1 plus square root of minus 3 over 2. Yeah, and then try to see whether this so q. So if we consider this field, then any other cyclic extension is obtained by adding a cubic root of an element here. Yeah, so where alpha is an element of this field. Yeah, we have, okay. And then we can try to
Excuse me, we did take a look at Gauss sum. And we know that gamma square is minus one. Well, it's
plus or minus p.
plus or minus p.
Mhm.
And what do we do with this information?
This means that gamma is so. What is gamma? Gamma is an element of our pith cyclotomic extension,
Mm-hmm.
and therefore we can well, we can call it gamma p, and this means that we can obtain square root of plus or minus p as an element of cycloatomic extension, and then for each prime we can obtain its square root as an element of cycloatomic extensions, and therefore we can obtain their product as an
Mm-hmm.
element of cycloatomic extension.
Okay, thanks.
And we know that all quadratic extensions are of this type, so that's it. Okay. Yeah, but with cubic it's less explicit because because mm, because you see it's yeah, so you see that it is so we get maybe let's call it L. We want a field which is so
And
what do we
we're
want?
also running out of time already. So,
You think we have to stop, yeah, here.
well,
All right.
let's finish this example and then stop.
Well, I'm not sure that we're able to finish this example, so maybe we can stop right now and discuss it some other day.
As you wish.
Yeah, because it's. I was going to show that it's how. I mean, it's well. I can say just a couple of words just to get to give an idea what is going on. So mm, we want this extension to be Z mod 3, and then we want what that is. Yeah, and you see that this is also. This is also a Galois extension
Uh,
of what yeah, maybe we
Barrel
should.
3, maybe.
I don't know. I mean, it's so you see that it is so this is again an extension of it is a cyclic extension of degree 3.
And as alpha, we take this 1 plus square root of minus 3 over 2.
Not no. That's the question. You see that there are many. So we want to describe all degree 3 cyclic extensions of Q. And but how could we do that? We in the case of degree 2 extensions, we just take square roots of something, of everything, everything we can imagine. Yeah, any rational number. But of course, you can reduce rational numbers. Instead of rational, you can restrict yourself to the integers because you can multiply by squares. But here also alpha runs. In principle, alpha can be arbitrary. Yeah, so it's uh, that's the question. What alpha could be so that this picture is possible. Yeah. So you see that. Um, mm, yeah. So this is a degree 6 extension. So this is degree 6, and degree 6 extension. So what is it is what are the groups of order 6? So groups of order 6. And what do we want from this group? We want that so we want that this extension is so we want this extension to be uh, this extension to be normal, yeah, and therefore um, this so this field should be this subgroup. So this is an extension of this is a Galois extension, as all intermediate extensions of order 2, and we want this subgroup to be normal. So this subgroup of two elements, and the claim is that groups of order 2 with a normal subgroup of order 2 are abelian. Normal subgroups subgroup of order 2 is abelian, that is isomorphic to Z mod 6.
With a normal subgroup.
Subgroup. Yeah, because you see that we want so this is a Galois extension. This one. So this maybe called G groups G. So it is of order 6, of course, because this is degree 2 extension, this is degree 3 extension, and yeah. So yeah, and all intermediates, all subfields correspond to certain subgroups, and but we want this extension to be normal. Yeah. So and this means that this subgroup should be normal in G. And so what are the groups of order 6? If this is a group of order 6, then yeah, so it means that the element, so if you have a non-trivial element, so sigma is non-trivial of order 2, yeah, and you see that if it is normal, then what does it mean that it is normal? It means that tau sigma inverse is sigma, yeah, for all tau. For in G, yeah, and so it means that sigma is central. So sigma is central, and well, and you also have an element. This is a group of order 6, so there is an element of order 3, and they commute, and therefore G is generated by sigma and tau, and it is isomorphic Z mod 2 times Z mod 3 as they commute. That's it.
And
okay.
This is why um, our groups of order 6. Oh wait, because Z modulo 6 is isomorphic to Z modulo 2 times Z modulo 3. Yeah.
Yeah. It's yeah. Of course, it's the same. Yeah.
Okay.
Okay. Yeah. So so. Okay, so now, yeah, but on the other hand, what happens? Yeah, so what I was going to say that what could be automorphisms of well, I'm not sure that it's an appropriate need more letters. So yeah, so if we consider automorphisms over automorphisms here, yeah, so this one. So yeah, maybe we should use to, yeah, to. because this decomposition, actually this decomposition is canonical, yeah, because this is we have so this sigma is uniquely defined because it is a unique element of order 2, and tau is defined up to inversion, yeah. So this pair tau and tau inverse is also uniquely defined, so we can think of tau is more or less uniquely defined, yeah. And now what is yeah, and tau is identical on so tau is identical on this quadratic extension, identical on q of square root of minus 3. Okay, and yeah, now what is this? This is it is an it is non this action is non-trivial, so it is multiplication by cubic root of 1, yeah. So this one, no, well, one of them, so maybe actually this is the choice of tau or tau inverse, yeah. So there is no difference. You can think of yeah, of this being more or less uniquely defined. So this one, and on the other hand, you can choose okay, yeah, and so what I'm trying to say is that yeah, maybe we should postpone because it's you see that it's we cannot prove much about uh, yeah, maybe we should postpone because it's a bit the argument is a bit complicated, yeah. So it's let's do this next time. Next time means in November, yeah. No, yeah, in November anyway, but in well, after the next week, yeah. Okay.
After the next week,
Yes,
I will
yes,
have. Well,
yeah,
we don't have a lesson the next week.
yes. So they are cancelled. Well,
Так, сейчас
for
еще
some.
раз. А в чем
Да.
причина? Куда у нас пропала пара?
Ну, ну так, в общем, так вышло. То есть я
А,
бы, ну, у меня просто у меня лично там не получается так
а,
поздно, в смысле, что вот я бы, то есть если бы народ смог собраться пораньше или пораньше, но не в среду, или там понедельник, вторник, то это можно было бы все переделать, вот, но, ну, в общем,
мгм,
я просто подозреваю, что это не очень реально. То есть мы уже пытались как-то собираться, но ничего не вышло, поэтому я даже не пытался как-то это перенести. Вот.
мгм, понял. Так, все, тогда я останавливаю запись.
Мгм.